So now let's take a step into, a little more abstract. We can ask the question, what are all the linear transformations where the domain is, let's say, R2? Okay? So in two-dimensional space, what are all the linear transformations? Which is, a bit of a harder question, because so far we've only been doing transformations where, intuitively we would imagine that they should be linear. So one way to go about it is to define matrix multiplication and then go from there. What we did before is we started with the intuition of what rotation should look like and then showed that matrix multiplication was a nice way to embody that, which is, I think, a great way to learn it. But let's just do it from the opposite direction. Let's define everything about matrix multiplication and then show it necessarily will be linear. So what do I mean by that? Well, we know how to multiply vectors and matrices, A, B, C, D, and multiply some arbitrary vector x, y. We can define this multiplication to be sort of you dot product the vector with the first row, and you dot product the vector with the second row, and there you go. Ax plus by, and then cx plus dy. So one way to do linear algebra is to define this to be true from the start as a definition. This is what we mean by matrix vector multiplication. And from this, you can prove a lot of properties. Mainly, it's linear, and that's where it sort of falls out of it. So the idea would be, suppose I had A, B, C, D, and I wanted to multiply this vector here. This vector was, x1 plus x2 and y1 plus y2. Okay, so now the vector that I'm trying to multiply in is, that plus that, and then that plus that. And if you do all the really annoying algebra, you get that I can sort of distribute matrix multiplication through addition. So this would equal A, B, C, D, x1, y1, plus A, B, C, D, x2, y2. Okay? And this property of, if this vector here is sort of x1, y1 plus x2, y2, the fact that the matrix sort of distribute among it, that's a consequence of this definition. You can do all the algebra and all the scut work and prove it. And the same thing would apply to scalar multiplication. So, for example, if I had A, B, C, D, and then I multiplied it by Cx, Cy, a scaled version of the input vector, then this would equal C times the regular A, B, C, D times xy. Okay, so these two, equations here, if you can even call them that, they are a consequence of the definition that we prescribed for matrix vector multiplication, and you can prove it rigorously if you really want to. But what this generally shows is that matrix multiplication by a vector is a linear map. This is pretty much the proof with all the scut work in between. The way this is generally notated in general, since we don't always have to be in R2, is, well, we can say, let A be a matrix. And for now, let's just keep it n by n matrix, but it could be any kind of matrix. N by n matrix. Then we can define a transformation using that matrix. Define a map T, and T is going to map, let's say, R2 to R2, so two-dimensional space Rn to Rn, n-dimensional space to n-dimensional space, okay, since there's n by n here, where T of x is any input vector from Rn, is given by the matrix vector product Ax. This is essentially how we're going to deal with linear maps forever, almost. Then, well, T is linear. because we just showed that matrix vector multiplication is linear. Okay? Mainly T of, let's say, the sum of two vectors. Right? Well, using our definition, it's going to be A times the sum of two vectors. But then we just, sort of showed previously, if you do all the scout work, that's just going to be AX plus AY. I can distribute the matrix through this plus sign. AX is just T of X, AY is just T of Y. So this is like a very almost over-explained way. And I can do the same thing with scalar multiplication too. T of Cx is going to be A times Cx. But then, we showed we can work it all out, do all the matrix multiplication. It's just going to turn out to be CAX, which is CT of X. So this, and these two conditions together constitute linearity by definition. But if you want, you can also look back at the previous videos we did on rotation and see how it all matches up. Okay. So that's why we have this idea where if you're a linear map, we can essentially just make you a matrix. And that will be linear. And it's not so entirely obvious. How do we know every linear map can be done by a matrix? I think just a good place to start now is, in general, if you're a linear map, there's going to be a matrix that does what you do, and that's what we're going to use. It gets more complicated because there are different vector spaces, and now the columns will end up meaning different things, but for the purposes of Rn to Rn, I think this is good enough. Just to end on an example, a larger example, Maybe T maps R3 to R3. Ooh. And then we define a matrix A to be, let's see, 1, 0, 0, 0, 0, 1, 0, 2, 0. Okay. And we define T of X to be AX for all inputs X. So T is a linear map by the definition that we've made it matrix vector multiplication. And we try to interpret what this is doing here. Okay. The first column is where the first basis vector was sent. So if we want to keep track, the first basis vector is going to be the x direction, 1, 0, 0. And this got sent to 1, 0, 0, the same thing. Okay, so essentially the x direction doesn't change. That's the same. The second column is where the second basis vector got sent, which is in the y direction, so it's 0, 1, 0. But this got sent to 0, 0, 1. The way to interpret this is the y component is getting turned into the z component. It's like saying whatever the y was, make it what z is, now make it what z is in the output. Because look, I'm just turning the y component, turning it into the z component. And lastly, the last column is where the z vector got mapped to 0, 0, 1. It got sent to 0, 2, 0. So this means take whatever the z component was in the input, and now make it into the y component and then scale it by 2. Okay? Scale it by 2. And we can use this to chalk out a few examples here. I'll keep the matrix on the board, but let's just take T of 3, 4, 5. And what's that going to become? Well, we established that the x direction doesn't change. 1, 0, 0 is sum of the 1, 0, 0, so this 3 component is still going to stay 3. So the output is still going to have 3 as the first component in the output vector. The y component became the z component. Oh, well, here's the y component, 4 in this case. It's z now, so it's 4 down here. And the z component becomes the y component scaled by 2. Here, the z component is 5. And now goes to the y component scaled by 2, it becomes 10. So t of 3, 4, 5 is now 3, 10, 4. And we can verify this using the matrix vector multiplication. We can just do it algebraically if you want to. Or t of 3, 4, 5 is 1, 0, 0, 0, 0, 2, 0, 1, 0, multiplied by 3, 4, 5. We can work it out. Dot product, and dot product. It's still 3, 10, 4. It's the same thing. So what I've done is, obviously it's more efficient to just do this computation, just do the matrix vector, multiplication. But you can also have done this by interpreting what these columns mean, right? And I think that's better for learning. It's like, 1, 0, 0 being the first column means 1, 0, 0 is still 1, 0, 0. That is the x component doesn't change. That's why the 3 is still there in the output. T of 3, 4, 5 is 3 is still up there. And then this means the y component becomes the z component because this is where y got sent. It was to 0, 0, 1 in the z. That's why the 4 here is now a 4 down here in the z place. And this is the other way around. The z becomes the y, but I scale by 2. 5 goes up here, and it becomes a 10, scaled by 2.